All right, so now we moving on to our next area of study, which is kind of the motion mechanics vectors, all kind of rolled into one. I'll split this up into 3 bits. So the first of the bits is the kinematics bit. So it's the motion stuff in a straight line. So we've got a few definitions of things. So, if you want to take notes and write these down, you need to stop the video and get them. So I'll probably go through them quicker than you can write. But anyway, so first of all, we'll start with the most basic thing, and that is position. And as it says, distance from a fixed point, one direction will be positive. So wherever that could be, left could be positive and right, then therefore right of that fixed point would be negative, or vice versa, or anything else you determine. So that's position. It's where something is from a fixed point. Then the next one is displacement. Now, displacement is related to position, but it's not the same. So here it is the change in the position. So it says here it has both a size and a direction, and things that have sizes and direction are vectors. Some symbols that you would see could be S or X. We'll use X a lot in this. Also units could be a whole bunch of different things. All right. And so just a note on that. The change in position, as it says there, is a vector. Distance is a scalar. So we'll talk about things, but when we look at examples, and we'll have a look at the things about distance and displacement, because there can be quite a difference in the number part of those depending on what's going on with the thing. And I'll go over that more when we get to an example. All right, so that's the first bit. And so then the next thing we look at here is velocity. And so here's a few things about velocity. So velocity, rate of change in position. So rate of change in position, so change with respect to time. All right, so time is what we're looking at. Change in position with time. So of course, change in position is displacement. So the average velocity would be delta x over delta t, the displacement over the time. Or displacement, of course, is our change in position. So our final x2 minus where we started off, x1 over the time. Now, instantaneous velocity, as opposed to the average, the instantaneous is given by this expression here. It's the limit as delta t tends towards 0 of delta x on delta t. All right, so you make this time span smaller and smaller and smaller, and you get to the velocity. Now, hopefully this kind of thing, well, maybe, I shouldn't say hopefully, but maybe you will, maybe you won't recognize it from way back when we did our calculus stuff, that this limit of the change in x with the change in t, or the change in y with the change in x, the limit as delta t tends towards 0 actually is the derivative. So the velocity is dx dt. So if you have an expression for position in terms of time, you get the velocity from differentiated. Again, we'll look at that in more detail when we do an example. So velocity has a size, forgot my E, and a direction, so it's a vector. And typical units, centimeters per second, meters per second, kilometers per hour, those sorts of things. Now, speed is not the same as velocity. Speed's a scalar, so there's no direction involved with scalar. And not only is it that, it also incorporates the distance travelled. So not the displacement, but the distance travelled. So the actual distance travelled. All right. And again, we'll go over that more on an example. So symbols for velocity v, of course. And sometimes you see x with a dot above it, and that is also velocity. So a negative velocity, as it says there, means travelling in the negative direction, whatever that direction is determined to be. Could be up, could be down, whatever it's determined to be. All right, this is handy to have. So if you've got something in kilometres per hour and you need to get it into metres per second, you divide by 3.6, and that's quite a handy thing to have. I would be putting that in my bound reference. And if you want, any great detail as to how that comes about, just ask and we can show you how it becomes 3.6. All right, so let's have a look at an example on those two things first. So distance, displacement, position, velocity, speed. Let's have a look at an example which incorporates those things. All right, so here's an example. So a particle moves in a straight line, so its position x from a fixed point O on the line at time t is given by, so here's our expression, xt, its position at any time t is t cubed minus t squared minus 8t plus 4. All right, and then we've got a bunch of things we're asked about. So part A says its initial position. So whenever you're looking at something that says initial is the start, and the start is time equals 0. So it's simply a matter of substituting 0 into our equation and calculating, and it is at 4. And it says centimetres here, x centimetres, so it's 4 centimetres from this point O. All right, initial velocity. Okay, so initial velocity. So again, that's time equals 0, but we've got to get the velocity. So remember, of course, the velocity is dx dt. All right, which in this case, we differentiate that expression. So 3t squared minus 2t minus 8. And then, of course, at the start, initially, the initial one, time equals 0, our velocity, we just substitute 0 in there. And so its velocity is negative 8 centimetres per second. All right. So the negative means it's going in the negative direction, wherever that is. All right. C asks us when and where. So whenever you see a thing when, that's time, and where, that's its position. Is its velocity 0? So we know that v equals 0. Now we've got our expression here for velocity. So our 3t squared minus 2t minus 8 is equal to 0. So we clearly need to differentiate this. Differentiate, what am I talking about? Factorise this. So 3t and t gives us our t squared. And 2 4s is 8. I'm minus there, so I'm going minus 2 and plus 4. So minus 6t plus 4t is minus 2t, so there we are, that's good. Then our null factor law says then that 3t plus 4 could be 0, or t minus 2 could be equal to 0. Now, if I rearrange this, take 4, divide by 3, so negative 4/3 seconds. Now, remember this now, kinematics, this is actually representing the movement of something. And so for kinematics, time starts at 0. So this here of negative time, that's kind of indicating that before we even started, something was going on, which of course doesn't make sense to have negative time. So we ignore the negative, and here if we add 2, time equals 2. So it's got a 0 velocity at 2 seconds. So when is 2 seconds? Where? Well, that's position. So we put 2 into that equation. And that's this one up here. All right, the t cubed minus t squared minus 8t plus 4. So it's 2 cubed minus 2 squared minus 8 times 2 plus 4. And when you work that out, you should get to negative 8 centimeters. So time equals 2 seconds. It's negative 8 centimeters from this point O. Right, average velocity in the first 2 seconds. So the average velocity, so D, the average velocity, the word average, not its actual velocity at a point in time, but its average over that would be our displacement over the time. And in the first 2 seconds, that displacement would be where it is after 2 seconds minus where it was at the start over the time, which is 2 seconds. Now we've figured out those things before. Negative 8 there for that, and initially was at 4. So negative 8 is where it is after 2 seconds, and 4 it was at the start. And so we've got negative 12 over 2, which is negative 6 centimeters per second for the average velocity over that time. All right, the next one, it says its average speed in the first 3 seconds. All right, so average speed, so E is our average speed. Now, average speed is our distance travelled. Over the time. All right. So, what do we need to know? Well, we need to know a bunch of stuff here. What we need to know is where this thing started. We know that its velocity at time 2 is 0, and that's at negative 8 then. We got that. So what do we need to know? We need to know where is it at t equals 3. So when we do that, then we can kind of figure out, well, what movement this thing's done. And then we can work out the distance. So of course that's 3 cubed minus 3 squared minus 8 times 3 plus 4. And so we got 27 minus 9 minus 24 plus 4. And when you work that all out, that's at -2 centimetres. So let's have a look and see what this thing's done. So I'm just going to draw a number line here. And there's our point O, that's 0. So 4 centimetres, and this is our positive direction up here. And then down the other way, this is the negative direction. And so let's now figure out what this thing's done. So at time equals 0, it was here at 4. Then at 2 seconds, it was at -8, right? So we figured that. It was at -8 down here at time equals 2. And then we've just worked out that at time equals 3, it's here. Oops, no, put that at the wrong spot. Let's get rid of that. Put it at the right spot. Let's put it at -2. So what has this thing done? Well, it must have gone, and of course in our time equals 0, I know it's going that way because at time equals 0, the velocity was negative. Right, so it was going in the negative direction. So I know at time equals 0, it goes there, and here, and so after 2 seconds, here it is. And we know that its velocity is 0 there because we figured that out in part C. At 2 seconds, it was at -8. All right, figured that out there. And so it must have, if it's velocity 0, it must have turned around there and it must come back. So that time equals 3, there it is. So now we're looking for the average speed. So it says it's the distance travelled, not its displacement, but its distance. So the actual distance it's travelled, well, it's gone 4 and it's gone all the way back here down to -8. So from +4 to -8, that's 12 centimetres. Then it's turned around and it's come back up here to -2, so that's 6 centimetres that it's travelled. All right, so our distance then would be the 12 plus the 6, which is 18. Not 16, 18. And so our average speed, let's get rid of that, don't need that. So our average speed is our distance travelled, 18, over our time, 3 seconds. So our average speed is 6 centimetres per second. All right. All right, so a diagram like this can be quite handy before you figure out what's actually happening with the particle, the thing, or whatever it might be. All right, next, acceleration. So here's some acceleration stuff. Some excuse me, definitions. So acceleration. So it says here it's the rate of change of velocity with respect to time. So looking at as we did before, the average is change in velocity over the time, which of course is the final velocity minus the initial over the time. And the instantaneous, of course, is the limit as delta t tends to 0, which of course is the derivative. Again, if you want to write this down, you need to pause. And of course, so that's dv dt. So it's derivative of velocity. Symbols, a or x with 2 dots. Acceleration's a vector, so it's got a direction. And centimetres per second, metres per second, and negative acceleration means we're slowing down. All right, so if you want more information about that, make sure you ask for any more information or clarifications. All right, let's look at an example. A particle moves in a straight line so that its position x meters from a picked point O on the line at time t is given by, here it is, t cubed minus 12t. So its initial velocity. So we're initial velocity. So first of all, our velocity dx dt should be 3t squared minus 12. And initial means t equals 0. So its velocity at time equals 0 is negative 12, and it's meters, so it's meters per second, x meters. Its initial acceleration. All right, so it's initial acceleration. So acceleration is dv dt. So here's our velocity, 326t. Is all it is. All right, so initial. Let's try and write it down here and see whether this thing chucks a wobbly or not. So initially is time equals 0. And so the acceleration there is 6 times 0, which is 0 meters per second squared at that time. All right. All right, so that's B. Part C, the acceleration when its velocity is 0. Okay, so we need to first of all figure out when the velocity is 0 before we can do that. So when its velocity is 0, so let's, when of course is the time. So C here. So it's chucked a bit of a wobbly there. So C here, velocity equals 0, and of course the velocity is 3t squared minus 12, isn't it, the velocity in terms of time? All right, so when 3t squared minus 12 is equal to 0, let's just rearrange here, 3t squared is 12, divided by 3, t squared is 4, so time is either plus or minus 4 seconds. Again, negative time makes no sense, so the time we're looking at is 4 seconds. And the question said, what is the acceleration at that time? Oh, hang on, I can't square root properly, can I? Square root of 4 is 2. So we want to know what the acceleration is at 2 seconds, and the acceleration, just reminding myself, is just 6t. So 6 times 2 equals 12 meters per second squared. All right. So there's an example of acceleration, involved acceleration. So here's another example here. But before we get to this other example, we're going to talk about things that are traveling vertically. Maximum height, at the highest point they get, the velocity is 0 momentarily. And now if you think about that, you think about this, as this goes up, for it to come down, it's got to slow down and then come down again. So right up here at that point, it's momentarily at rest. So you've got this thing here, throw it in the air, comes back down. So momentarily here, so momentarily it's at rest. Of course, gravity's pulling it down, so it's slowing down, slowing down, slowing down, momentarily at rest, then it falls and speeds up, speeds up, speeds up. All right. So you can, for things traveling vertically under gravity, you can use that relationship. All right. So you don't need to actually be told that. That's something that we know. So again, something you should have in your band reference to remind you. So here we go. Here's a particle projected upwards from the top of a 40-metre high building. So that its height x meters above the ground. So ground above the ground, x meters above the ground. So here's our building, and that's 40 meters high, and it gets projected from up here. And here's the ground, and the ground is x equals 0. All right. So initially, at time equals 0, it's up here. So at time equals 0, x is 40. Now, I haven't actually mentioned this, but I will now. I always choose, for vertical stuff like this, I always choose that up is the positive direction. All right, and so that then means down. If something's going down, it would be the negative direction. All right, so for vertical motion, there are two directions. There's up and there's down. And I always choose up to be positive, and I don't deviate from that. That way I don't confuse myself from question to question. All right, so, and here's our thing, xt equals 40 plus 24t minus 4t squared. And the question says, find the maximum height above the ground. All right. Here's our expression in terms of time. So if we throw this, it's going to go up and then it's going to go down. So what we're interested in here, what is it? Its position there. So what we're going to need to know is we're going to need to know the time. And how are we going to work out the time? Well, we're going to use this here, that at the maximum height, v equals 0 momentarily. So here, the velocity will be 0, and the time, I don't know what it is, but when we find it, we can put it into there and find out how high we are above the ground. All right, so the velocity then is the derivative. So 24 minus, bring the 2 down, multiply 8t. And we're interested when the velocity is 0. So 24 is equal to 8t. And 8 goes into 24 3 times. So the time is 3 seconds. So it's 3 seconds. Since we chucked it, it's 3 seconds to get to the highest point. We want to know what that height is above the ground. So we need to know x at 3. So that's 40 plus 24 times 3 minus 4 times 3 squared. Yep, that's right. And so that, when you work it out, is 76 metres. So it's 76 metres above the ground is its maximum height. All right. Okay, so I've just done derivatives there. So you do derivative, you can get from x, its position, differentiate, you get to velocity, differentiate, you get to acceleration. Of course, we could go back the other way as well. And of course, if we go back the other way, if we differentiate to go this way, we would anti-differentiate to go that way. And so antiderivatives that we're interested in are these ones here. So since the velocity is dx dt, if we've got the velocity and we want to go back to x, that would be the integral of v dt. And for acceleration, seeing as that's dv dt, if we want to go back the other way and find velocity, we would anti-differentiate the acceleration. Okay, so let's have a look at an example. The acceleration of a particle moving in a straight line in meters per second squared is given by that. Acceleration is cos pi t. Okay, so they don't have to be polynomials, they can be any kind of function. And we're told the initial velocity is 3 meters per second, so that's t equals 0, v equals 3. And its initial position is 6, so t equals 0, x equals 6. And so what we are after is to find its position at any time. So if we've got acceleration, we need to anti-differentiate to get velocity, then we need to anti-differentiate again. And we've got some information to find our constants. All right, so let's have a look. So our velocity then would be the integral of cos pi t dt. And then when we did that anti-differentiation, cos will come from sine, and we've got a constant in there, so 1 on pi, plus c. Now to find c, we use this information. So t equals 0, v equals 3, so 3 equals 1 on pi, sine of 0 plus c. Of course, the sine of 0 is 0, so that then means that c is 3. So we now have our velocity expression, which is 1 on pi sine pi t plus 3. Then, if we want to go to position, we would then need to anti-differentiate all of that stuff. 1 on pi sine pi t plus 3, and we're anti-differentiating all of that with respect to time. All right, so we can do each term individually. All right, so cos pi t. Now, of course, when we differentiate cos, it goes to negative sine. There's no negative here, so we need a negative. And of course, we've got to go 1 over the constant here, which is pi, so we've already got 1, so we're going on 1 on pi squared there. And the 3, of course, it just becomes 3t plus some constant. I'm going to call it d so we don't get confused about the one up there because it's a different one. And what were we told? We were told that the initial position is 6, so t equals 0, x is 6. So t equals 0, x is 6. So 6 equals negative 1 over pi squared, cos pi times cos of 0 plus 3 times 0 plus d. So 6 equals, cos of 0 is 1, so negative 1 on pi squared plus d. And so d, I was probably going to chuck a wobbly, I've gone into the next page. So d then would be equal to 6 plus, forgot my squared, 1 on pi squared. All right, so let's put all of that together there. So my position then would be negative 1 on pi squared cos pi t, so I'm looking up here, plus 3t plus the d, and the d we found out to be that. So plus 6 plus 1 on pi squared. All right, so these equations can be kind of funky in a way. All right, so that's the first part of the kinematics. So using some of our calculus that we differentiation and our integration that we've looked at. So if there's anything in there you're not sure of, make sure you ask for a bit of help. And as always, have fun.